Welcome back. Today we are tackling a fantastic question from the 1988 China Math Olympiad concerning quadratic roots. Here is the problem. We are given a relationship between three real numbers, p equals q1 plus q2 plus 1. Using this single clue, we need to prove that at least one of these two quadratic equations has two distinct real roots. Before we get lost in the algebra, what does it actually mean to have two distinct real roots? Let's picture it geometrically. Think of a quadratic equation as a U-shaped curve, a parabola. The real roots are simply where this curve crosses the x-axis. Let's look at the famous quadratic formula. The roots depend entirely on what is underneath the square root. We call this piece the discriminant, represented by the Greek letter delta. Let's see this in action. When the discriminant is negative, the square root breaks, and our parabola floats above the axis. No real roots. When delta is exactly 0, the plus-minus does nothing, so it touches the axis exactly once. But if delta is strictly positive, the square root works. The plus and minus gives us two distinct paths, crossing the axis twice. Going back to our problem, we have two quadratic equations. For at least one to have distinct real roots, we simply need to prove that either delta 1 is greater than 0, or delta 2 is greater than 0. Let's calculate the discriminants. For the first quadratic equation, b squared minus 4ac gives us delta 1 equals 1 minus 4q1. For the second equation, applying the same formula gives us delta 2 equals p squared minus 4q2. Proving either one of these is strictly greater than 0 directly is incredibly tough. But here is the big trick. Let's analyze their SUM. We can group the matching terms together. Factoring out negative 4 gives us p squared plus 1 minus 4 times the quantity q1 plus q2. We ended step 2 with this key equation. Notice the purple piece, q1 plus q2. Can we simplify it? Let's go back to the original question. Remember, we were given that p equals q1 plus q2 plus 1. This means q1 plus q2 equals p minus 1. Let's substitute p minus 1 back into our sum equation. Expanding this gives p squared minus 4p plus 5. And by completing the square, we brilliantly get p minus 2 squared, plus 1. Here is the ultimate punchline. Because any real number squared is always 0 or positive, p minus 2 squared is at least 0. If we add 1 to it, the entire expression must be strictly greater than 0. Therefore, delta 1 plus delta 2 is strictly greater than 0. If two numbers add up to a positive value, it is physically impossible for both of them to be negative. Therefore, at least one of our discriminants must be positive, meaning at least one equation must have two distinct real roots. And just like that, the proof is complete. A brilliant example of mathematical logic from the 1988 China Math Olympiad. See you next time.